Welcome to Hot Chips 33. Session 7. Graphics and Video.
Good afternoon, good evening, and good morning, since we are virtual again. I'm Pradeep Dubey, part of Intel Labs and Director of Parallel Computing Lab, and your session chair for this exciting session on graphics and video chips. I'll start with a reminder that you are highly encouraged to use Slack channels to interact with our speakers and our other attendees. I've already posted each speaker's bio, more detailed bio in the Slack channel, so I'll be brief here. More importantly, you can use Slack channels to ask your questions, show your support for questions someone else may have asked. I'll pick a subset of these questions in the Q&A session. So let's get started. First talk in our session comes from Intel's David Blythe. He's Intel's Senior Fellow. He'll walk us through Ponte Vecchio GPU architecture. He's also Director of Graphics Architecture. So without further ado, David.
Thank you, Pradeep. Today I'd like to talk about one of the most ambitious and complex projects ever conceived and implemented at Intel, the Ponovecchio GPU. But before I get started, I'd first like to acknowledge that this has been a large team effort and that I feel privileged to come and present this information on behalf of the Intel GPU team and our partners. We started this project several years ago with ambitious goals: to increase the amount of GPU compute by over 500 times what we had previously implemented in an Intel GPU, coupled with the necessary memory bandwidth and capacity to feed that compute. To be able to connect multiple instances together with high-speed interconnect to further scale up the processing power into larger compute nodes. And most importantly, to create a full software stack to support the needs of HPC, AI, and data center workloads. Today I'll cover the core architecture of the Ponovecchio GPU and some of the technology and engineering work needed to build it. Before diving into the GPU architecture details, let me provide some more context and a bit of an architecture recap. Around this time last year, Intel introduced the XE architecture, and we discussed variations of that common architecture or microarchitecture to support the needs of different market segments. At Hot Chips 2020, we outlined the 4 variants: XELP for low power, XeHPG for high-performance graphics, XeHP for scalability, and XeHPC for compute density. In that talk, we overviewed some of the baseline XE architecture. In this talk, we'll shift to the other end of the spectrum and describe more architecture details of the XeHPC architecture that powers Ponovecchio. For the HPC exascale market, we needed the architecture to scale up the compute power and memory bandwidth, and to also increase the compute density while supporting a broad set of data types. We broke this problem down to 4 hierarchical building blocks: core, slice, stack, and link. Let me walk you through each of them, starting at the innermost block. First, I want to introduce the XE core. It's our foundational processing unit through which we scale our architecture. Now, many people who have followed Intel GPU architecture are used to us discussing execution units, or EUs, and EU counts as the innermost block. As we evolve and scale up the architecture, we believe that it makes more sense to describe the compute subarchitecture at a coarser level of detail, and this will simplify some architecture comparisons. XE cores are highly efficient arithmetic machines. In each XE core, there are 8 vector engines. Each vector engine provides floating point and integer operations on 512-bit wide vectors. There are also 8 matrix engines, referred to as XMX or XE matrix extensions. Each XMX engine is built with an 8-deep systolic array. XMX performs 8 sets of 512-bit wide vector compute operations per clock. These vector and matrix engines are supported by a wide load store unit that can fetch 512 bytes per clock. Each XE core has a large 512 kilobyte L1 data cache, currently the largest in the industry. We optimize the XE core for large datasets, and this big L1 cache helps tremendously. The L1 cache also supports a scratchpad partition whose size is software configurable. The scratch pad is also known as shared local memory. High arithmetic rates for critical data formats are essential for high-performance computing and AI applications. On the left and right are the architecture rates for various data types on the vector and matrix engines. Now, simply multiplying by clock frequency gives an idea of peak rates, but it's not the whole story, as the XE core can co-issue instructions to exceed these single op per clock rates. Our Intel libraries and kernels take full advantage of this for increased performance of the XE core. The next little building block is the slice. For XE-HPC, a slice has 16 XE cores, totaling 8 megabytes of L1 cache, 16 ray tracing units, and supports independent execution of one hardware context. The ray tracing units provide fixed function computation for ray traversal, bounding box intersection, and triangle intersection. This makes XE-HPC very attractive for professional visualization and content creation applications. The hardware context feature implements space sharing as opposed to time sharing, and enables XE-HPC GPUs to execute multiple applications concurrently without expensive software-based context switches. This greatly improves the utilization of GPUs in the cloud. At the top level, we have the stack. This can be a full GPU in itself. A stack contains 4 slices. This adds up to 64 XE cores, 64 ray tracing units, and 4 hardware contexts. The stack also has our massive L2 cache and XE memory fabric. By the way, I want to mention that in prior Intel GPU architectures, the L2 cache was called an L3 cache. There are historical reasons for the choice, but for all practical purposes, it's really an L2, and us renaming it to L2 aligns better with the rest of industry. Now, the stack also contains 4 HBM2E controllers, a state-of-the-art media engine, and 8 XCLinks. The XE memory fabric connects copy engines, the media engine, XCLink blocks, HBM, and PCIe. The XE-HPC architecture supports additional scalability by allowing multiple stacks to be connected together. The architecture supports it through the flexibility of the XE memory fabric, allowing stacks to be connected directly together using advanced packaging technology. The XE memory fabric extends unified coherent memory across multiple stacks. This can dramatically simplify the software developer's task of managing data structure consistency. Employing one or more stacks, we can now deliver leadership compute and memory bandwidth for a wide range of HPC and AI systems with a single design. The fourth dimension to our scaling strategy is our XCLink connectivity architecture. XCLink extends the high-speed coherent unified fabric for inter-packaged GPU to GPU communication. It supports load store, bulk data transfer, and synchronization operations. It includes an 8-port switch, enabling up to 8 fully connected GPUs in a node without any additional components. This leads to the ability to build very flexible topologies. Since it's easier to show than tell, here are some examples from left to right. First is an XCLink between 2 XE-HPC GPUs, so we could connect them with up to 8 XCLinks. Next, we show scaling to 4 GPUs for larger problems, and this is a popular configuration. Third, we have the 6 GPU per node configuration, and this may look familiar as this topology is the one that is used in the Aurora's Accelerator network. And on the right, we have 8 GPUs. This can be implemented in a compact form using the Open Compute Project OAM form factor for the GPU and a baseboard to connect the GPU modules together. The flexibility of XCLink enables a high number of coherent and unified accelerators in a node with no need for additional components to scale up. This concludes our walk through the major elements we use to create a highly scalable architecture in XE-HPC. We believe that it allows building huge GPUs, the magnitude of which has never been built before, as far as we know. So now we have described our architectural approach to scalability. Let's talk about building a massive GPU, the Ponovecchio implementation. At the beginning of the talk, I stated that Ponovecchio was one of the most ambitious and complex projects done at Intel. Much of the complexity manifests itself in the engineering and implementation work. That's probably a kind way of saying the architects created a nice XE-HPC definition, but left the really complicated work to the engineering teams. I'm grateful and delighted to acknowledge my colleagues and partners in the IP and SoC engineering teams, as well as packaging, process technology, and manufacturing, who all enthusiastically took up the challenges and overcame them to bring this chip to life. I'll describe some of the highlights of the work that was undertaken, and I'll point out that Ravi and Sandeep also discussed some of the packaging work in the advanced packaging tutorial on Sunday. Now, it's a bit of a misnomer, or at the very least an understatement, to call Ponovecchio a chip. We struggle a bit internally with how to talk about it in an unambiguous way. It's a collection of chips that we call tiles that are woven together with high bandwidth interconnects and that are made to function like one monolithic silicon. The mechanics of weaving these tiles together introduced multiple challenging problems that had to be solved. My colleague Masuma Bawala, who leads the silicon engineering team, says planning Ponovecchio execution was a completely different paradigm. And I think that's an understatement. In a new chip project, it's common to change one or two of the ingredients, such as architecture or power delivery or verification. But all of my engineering friends say that it is unprecedented to have to change this many aspects within one project. And that was the challenge that was building Ponovecchio. As you see in this exploded view, Ponovecchio comprises several complex silicon designs that are implemented as tiles: compute tile, Rambo or cache tile, XCLink or connectivity tile, and a base tile that binds together these other tiles along with high-speed HBM memory. The compute, Rambo, and base tiles are assembled into a stack using Foveros packaging to create the 3D stacking of active silicon for power and interconnect density. Embedded silicon bridges, EMIB tiles, enable planar, low-power, high-speed connections from the 3D stack to the XCLink tile into HBM memory. EMIB tiles also carry the MDFI interconnect traffic between base tiles, allowing further scaling from 1 to 2 architecture stacks. All of this comes together in a manufacturing tour de force across several different process technology nodes. The combination of multiple complex technologies in Ponovecchio gave rise to a number of challenges, some expected, some discovered along the way. Let's walk through a few of the bigger challenges. Foveros was critical for Ponovecchio 3D stacking, and we learned many things about both functional and physical implementation. For example, we had to transfer data at 1.5 times the speed over our original plan to reduce the number of Foveros connections. We also had to lock the Foveros locations early in the design on all tiles, which meant that the floor plan was locked very early. Since we pioneered this large-scale multi-tile 3D implementation, we had to innovate continuously on die-to-die implementation and verification methodology. We developed many tools, methods, and scripts in real time, and performed validation at multiple levels of hierarchy with new BFMs and test benches to keep the tiles independent and keep the hierarchies clean and crisp. This facilitated an independent schedule for each of the 4 main tiles and enabled their own debug packages. With this divide and conquer approach, we were able to stage both pre- and post-silicon validation, such that the chip booted within a few days of the SoC package assembly. The stage approach, while essential, meant that the RTL versions of the various tiles had to be in sync for the integrity of the top-level model. The high-power multi-tile package posed its own challenges related to signal integrity, reliability, and power delivery, as there was no precedence, internal or external, to Intel. Foveros implementation was complex and time-consuming, because Ponovecchio has 2 orders of magnitude more Foveros connections than any previous Intel design. All the electrical and physical collaterals had to be generated from scratch and verified prior to delivery to our partner teams. While Ponovecchio was a challenge in aggregate, individual tiles each had a level of design complexity of their own. Now let me tell you about some of the more complex Ponovecchio tiles. The compute tile is a dense package of XE cores and is the heart of Ponovecchio. One compute tile has 8 XE cores with a total of 4 megabytes of L1 cache. It's our key to delivering power-efficient compute. It is built on the most advanced TSMC process technology called N5. The tile has an extremely tight 36-micron bump pitch for 3D stacking with Foveros. We paved the way with the design infrastructure setup, tool flows, and methodology for this node at Intel. The base tile is the connective tissue of Ponovecchio. It is a large die built on our Intel 7 process optimized for Foveros technology. It is where all the complex I/O and high bandwidth components come together with the SoC infrastructure: PCIe Gen 5, HBM2E memory, MDFI links to connect tile to tile, and EMIB bridges that challenge physics. The sheer amount of high bandwidth 3D and 2D interconnect, along with low latency, makes Ponovecchio a massive connectivity machine. And perhaps not surprising, implementation of this tile was the hardest design challenge on Ponovecchio. We worked closely with the Intel technology development team to match the requirements on bandwidth, bump pitch, and signal integrity. The XCLink tile provides the connectivity between GPUs, supporting 8 links per tile with 4 lanes per link. It is critical for scale-up for HPC and AI. We are targeting the fastest SerDes supported at Intel, up to 90 gig. When we won the Aurora Exascale supercomputer contract, this was a new tile added to enable the scale-up solution that met the requirements. We built this tile in less than a year. Ponovecchio is designed to be in PCIe cards with XCLink interconnect bridges. The OEM module form factor will be integrated into carrier baseboards that bring together multiple GPUs with XCLinks. Our OEM partners will provide various accelerated compute systems integrating these Ponovecchio subsystems along with Sapphire Rapids. Last year in his Hot Chips 2020 keynote, Raja Kaduri spoke about the challenges in programming modern heterogeneous architectures. Building powerful hardware is only part of a complete solution. Application, middleware, and library developers need an effective environment for creating and deploying software. So providing a productive software development system was an important part of the XE-HPC architecture and Ponovecchio design and development. In the spirit of the keynote last year, Intel took a broader approach to the problem and created a programming framework that lets software developers transparently program for any mix of CPUs and accelerators, called OneAPI. It specifies a common hardware abstraction layer, data parallel programming language, and comprehensive collection of performance libraries addressing math, deep learning, data analytics, and video processing domains. OneAPI is an industry initiative that provides an open, standards-based, unified software stack that is cross-architecture and cross-vendor. I won't be going into more detail, other than to say that OneAPI provides a comprehensive software framework for programming Ponovecchio and is running on the A0 silicon. No doubt that you have all been waiting to hear some performance data. As I mentioned earlier, we have A0 silicon, which is our first stepping. This two-stack system already produces greater than 45 teraflops of sustained vector single precision performance, validating that our compute tiles are healthy. We also measured greater than 5 terabytes per second of sustained memory fabric bandwidth, which validates our Foveros 3D packaging technology, and over 2 terabytes per second of aggregate memory and scale-up bandwidth, and this proves all our EMIB bridges are very healthy. We also have some early machine learning workload measurements. ResNet 50 inference throughput on Ponovecchio with Sapphire Rapids exceeds 43,000 images per second, and ResNet 50 training throughput exceeds 3,400 images per second, both surpassing the standard you see today in market. We started on our vision several years ago with ambitious goals for Ponovecchio. It's an incredible moment for us, seeing this extraordinary silicon engineering effort and the ambitious software initiative come to life in our labs. We still have a ways to go, and we're not done yet, but we can't wait to bring this architecture to all our customers early next year.
Thank you, David. Let's move to questions now.
Okay.
The first question here comes from Joshua Gregory, editor Chips and Cheese. It says, you mentioned that Ponovecchio has 45 teraflops of FP32 compute, but earlier in the presentation you said FP64 ops per cycle is equal to FP32. Does this mean that Ponovecchio has 45 teraflops of FP64 in A0 silicon as well?
Architecturally, yes, that's the capability. You know, that in practice the performance might vary a little bit just because of the number of toggles might be different and memory bandwidth consumption, things like that. But yeah, they should be very similar.
Okay. Second question comes from John Masters from Red Hat. Can you talk about multi-vendor foundry collaboration and any challenges you have found specific to that?
I think it's probably more organizational than anything else. Probably the most interesting one, was and successful was having the compute tile work well with the base tile. and making sure like the bump pitches would line up and that we could do all of the Foveros connectivity. For other things, like Intel actually has a history of doing some multi-foundry stuff and doing planar interconnect. So there's some methodology and best practices for interacting with in multi-vendor collaborations that we've already sort of got to work pretty well.
Okay. Next question from Ritika Borkar, NVIDIA. Could you share more insights about hardware context? Does a programmer view Ponovecchio as a monolithic device, or 8 hardware contexts across 8 slices implies support for 8-way multi-tenancy by independent users as well?
Yes, it looks like a single logical device that supports the. It's more that independent applications can run with some level of isolation at the context level from one another. But it doesn't look like 8 independent GPUs at the device driver abstraction level.
Okay. Next question. Just trying to see. I just saw it. Yeah. How do you debug the from Power New TSMC? How do you debug the Ponovecchio chip with 47 chips packaged together with email and Foveros?
Well, the obvious answer is very carefully, but more seriously, like when the whole thing is together, it really does look like one logical GPU, and so we debug it fairly similar to that. If we start to find hardware issues, we may narrow it down to a particular tile and then do independent debug on that tile. But that's actually not really any different from how we would do hardware debug on a monolithic design, in that we'd be isolating it down to functional units or clusters, or down to the smallest unit that we could to go reproduce the problem.
Okay, next question from Paul Alcorn, Tom's Hardware Media. Does Ponovecchio XCLink support the CXL? And if so, which revision?
Doesn't like the CXL 1.0, 1.1 spec is actually a pretty complex, PCIe-like protocol. What we're using for XCLink is simpler than that, but there's probably an interesting question about, for us to look at around standardization and whether it can fit into the CXL family, and that's something that we're still thinking about.
Okay. So next, let me ask you, what was the most difficult aspect, architecture or implementation of PVC?
Well, from an architecture point of view, it's probably making it scale while maintaining efficiency. And it's something that we had some experience, first round with doing XEHP, which we talked a little bit about last year, but we sort of dialed it up a notch. And then from an implementation point of view, I'd say probably the way that we stressed and pushed for the Foveros technology, well beyond where it had been used before, it made it a particularly interesting challenge.
Okay, there's just a couple of more questions I'll ask because many people are asking for this. Does PVC connect to SPR using CXL or PCIe? I guess, go ahead.
It definitely does PCIe. I think we haven't actually disclosed about the CXL side yet.
Okay, and then another question: can you comment on XCLink bandwidth?
It's the up to 90 gig, times 4 ports, times 4 lanes. Is the per XCLink.
Last question. Did we see expected peak power / TDP?
Sorry, I didn't quite catch it.
But yeah, they're asking expected peak power / TDP from Ian Curtis and Antec.
Yeah, we're not actually giving out the exact TDPs. Ian probably knows this from me, that I'm trying to stay away from product specifics versus what's the architecture capable of.
Okay, so that should do it. Thank you, David.
Okay, thank you.
Thank you. And there's more questions in Slack channels. Please go ahead and keep asking. David will find time.
Yeah, and I'll I'll answer, and my colleague Hongjiang will help as well with whatever's out there on the Slack channel.
Thank you. So now we move on. We move on to our second talk, and this talk comes from AMD, right? More specifically, their new graphics architecture, RDNA 2. And speaker is Andy Pomianowski. He is an AMD fellow and corporate VP of product architecture in Radeon Technologies Group. Prior to this role, Andrew spent 4 years working at Apple as their graphics performance architect. And he rejoined AMD to lead graphics architecture development for the Xbox Series X, Series S, and now is driving AMD's graphics product roadmap. So, Andy?
Hello, I'm Andrew Pomianowski, fellow and Radeon product architect at AMD. And I'm excited and honored to be here at Hot Chips with the opportunity to present the work of our team on the RDNA 2 graphics architecture, which we built to form the basis for next generation gaming experiences in consoles, PCs, and beyond. Before we get started, I'll just note the usual cautionary statements regarding the information that I will be presenting today. When we developed the RDNA architecture, its name came about because we had made the decision to split our architectural development into 2 primary tracks. One of those tracks was designed to provide the foundation for the high-density computational capabilities required for HPC and data center, called CDNA. The other track was RDNA, aiming to provide the best platform that we could create for gaming and other consumer experiences. This should not be taken to mean that RDNA is lacking in efficiency when it comes to computation, far from it. But we saw sufficient differences between the primary optimization points for the 2 markets that we did not want to be forced to compromise the decisions for one set of products with architectural necessities required by the other. There's a quote often used that refers to the development of the F-15 Eagle fighter aircraft, "Not a pound for air to ground," a clear statement of the core philosophy of the design which drove the major decisions. And we wanted to adopt a similar clarity of direction up front with RDNA 2. Our goal was to create a gaming architecture with the highest performance per watt that we could achieve. And this direction helped us remain focused as we could align with that North Star whenever we had difficult decisions to make. That firm core direction did not prevent us from creating a truly flexible and adaptable design. Focusing on the fundamentals and creating a sound architecture with great foundations resulted in products that are capable of remarkable things. Our time today is short, and a deep dive into all of the innovations that went into RDNA 2 is not really practical, but I will aim to give insight into the core tenets of the design, why we made particular decisions, and how those came together in the final products. The RDNA 2 architecture came to market less than 18 months after the release of our first RDNA products. And prior to this, our GCN architecture had been very successful, powering broad graphics and computational experiences in many markets. But RDNA itself had been a major and necessary architectural development, establishing a new core based on multiple generations of learning. As we worked through the process of bringing RDNA to market, we had already identified the key areas we wanted to concentrate on with the next generation design. Any graphics architecture is going to require advances in computation, throughput, bandwidth delivery, and practical features, and we formed ambitious plans in all of those areas. Firstly, we felt that there was a lot of opportunity to enhance the frequency attainment of the design. RDNA had unshackled us from certain architectural underpinnings and limitations of GCN, and with a focus on both logical and physical design improvements, we felt we could achieve some real breakthroughs in GPU frequency and performance. Achieving increased frequencies at lower voltages would clearly lift all boats, scaling the overall design upwards in performance per watt, which was our key metric. To balance this effort, we would also need to minimize wasted power in the design, which would allow us to tap into as much of that frequency attainment as possible. So we put an intense focus into clock gating effectiveness and minimizing switching capacitance to achieve as much leverage here as we could. In looking at memory technologies, we arrived at the conclusion that some bold steps were needed to establish a forward-looking architecture. A consumer graphics product must rely on widely available commodity memory to deliver bandwidth at acceptable cost, and those memories consume significant power. We wanted to create a memory architecture that could operate effectively while minimizing external bandwidth and power to reach the broadest range of applicable products. And finally, we were very aware of the need to build an advanced feature set. as developers were now becoming more familiar with the major shifts in graphics APIs that had occurred with DirectX 12 and Vulkan, and they were now ready to develop new engines and experiences for their users. Our position developing the next generation of console architectures gave us an opportunity to play a key role in establishing core principles and a rich tool set for the next wave of rendering technologies. Let's take a look at the high frequency design first. This was one of the most key decisions that allowed us to achieve our performance uplift. In any new graphics architecture, we can aim for improved performance either by delivering more throughput each clock or by increasing the attainable clock frequencies, and all designs must inevitably pick some mix of these. In the case of RDNA 2, we felt that frequency attainment could form our primary lever, along with a focus on delivering strong performance scaling with that frequency. Naturally, we also aim to achieve additional streamlining and improvements in the throughput of the design as well, but we felt that the clear direction on frequency would provide alignment for our teams and create the heart of RDNA 2. Maximizing attainment here would benefit all areas of the design equally, delivering a well-balanced architecture. Outlining this path early in the design gave our architects a clear set of priorities as they moved from RDNA to RDNA 2, and achieving an efficient high-frequency design required careful consideration, as the constraints involved can affect many downstream architectural decisions. The RDNA pipeline had been designed to be better positioned than GCN to attain higher frequencies, and our first generation had scaled to speeds of about 2 GHz. But analysis showed that we had the headroom to achieve a generational uplift in both efficiency and performance without a change in process node and without causing large area increases in the design. Graphics processors had been making only gradual increases in achieved frequencies for a number of years, but RDNA had positioned us to move decisively past these restrictions. We brought in expertise in physical design from our CPU organization, and our graphics team began an intensive effort in improving levels of logic in the design. The end results of these efforts and this architectural choice speak for themselves. In one generation, on the same technology node, we gave ourselves the flexibility to push our attained frequencies more than 30% higher than the previous generation, or conversely, to achieve the same frequencies as the previous generation at less than half the power. This gave us the ability to produce very large RDNA 2 parts while remaining power efficient. The Radeon 6900 XT has twice the compute units of the 5700 XT from the previous generation and runs at much higher frequencies, but still fits into a typical historical power envelope for high-end graphics hardware. Now, with the fundamentals of the very high throughput of the engine out of the way, let's move to how we approached the solution for bandwidth delivery. The Radeon 5700 XT had been equipped with a 256-bit GDDR6 memory interface at 14 gigabits per second. But as we moved to our next generation, we were going to be pretty much doubling the performance level of that part, placing a lot of pressure on memory throughput. A 512-bit GDDR6 interface was quickly rejected as impractical. Moving to a 384-bit interface with increased memory frequency was an available option, but it was not well aligned with our targets for power efficiency. GDDR memory consumes significant power, and with the very high frequency flexibility we were creating, stealing power away from the core and sacrificing it to shift data across a wide memory interface was not an attractive option. With the key principle of driving higher performance per watt from the architecture, we found ourselves choosing a new path. When we analyzed the data from our key applications, we felt we could plot a route that was both more efficient and that aligned with providing compelling capabilities for future graphics and compute applications. If we go back a number of years, GPU rendering originated as pretty much a one-pass activity. The geometry for the scene would be fed in, and the GPU would shade the triangles and write out image data. In GPU designs, the cache hierarchy was primarily built to hide latencies, capture short-term spatial reuse of data, provide bandwidth amplification, and support intermediate processing steps such as texture decompression. But it was not really built with a view to extracting significant temporal reuse. The state of the art has naturally moved on a great deal, and modern rendering and computation paradigms on GPUs show activity dominated by complex multi-pass algorithms. The GPU generates data in one pass and then uses it as input to one or more subsequent passes to generate a final image. So, we asked what we would need to be able to capture the data from each pass and feed it forward to the next. And when we looked at examples from multiple applications, it showed that in combination with modern GPU data compression, a cache that could capture a majority of temporal reuse was practical. if we took advantage of the technologies available to us. Our final design therefore took shape to take advantage of dense SRAM technologies that we were already developing within AMD. The caches being developed for our EPYC server CPUs could achieve 4 times the density of our traditional GPU L2, and were viewed as an ideal building block for a new level of cache with an order of magnitude higher capacity than what had gone before. The cache capacity for each member of the RDNA 2 family could be tailored around the primary goals for that device. And by putting the majority of the bandwidth delivery for the core itself onto the die, not only could we reduce the power used for external memory, but also provide bandwidth amplification that could scale directly with the fluctuating demands of the compute units. In the RDNA 2 design, as the frequency and bandwidth demands of the core change, the frequency of the data fabric and cache can also change in an agile fashion to match the measured needs. Retraining and other complexities in managing external memory, such as delivering guaranteed quality of service for displays, can limit the ability of GPU memory interfaces to change frequency in real time, but few such limitations apply to a high-capacity cache. Not only that, but for workloads that can fit fully in the cache, our architecture can offer around 4 times the bandwidth of the external memory, while delivering that data with far lower latency and power. The cache is built to work even with applications that are completely unaware of its presence. But as we move forward, we believe it will be completely natural for applications to start to take advantage of the availability of fast, low-power local storage to increase their efficiency even more. Looking at the overall benefits that we gain in the architecture, we can see the following. The first and most obvious benefit is that we deliver the frame data with much lower NG per bit when compared to the equivalent bandwidth with a wide external memory interface. Here, we show the bandwidth and corresponding power consumption for different widths of GDDR interfaces based on our measurements, and we've plotted the attainment of the infinity cache for a Radeon RX 6800 for typical workloads rendered at 4K resolution. We can keep the engine fed with very high effective bandwidth, but the cache contributes only a small amount of additional power over the 256-bit GDDR6 interface. A second benefit from sourcing most of our bandwidth from non-die cache is in delivered latency. It's intuitive that a large design like the RX 6800 has further to route on die to the memory, and will therefore have higher average latency. And that incurs costs both in the power consumed as the bits are shuttled around, and the engine buffering required to overlap work and remain busy while threads are waiting on their data to return from memory. With the infinity cache, we source most of our memory accesses directly from the on-die SRAM, so that our effective latency to memory is lower. For the common case where data can be found in the cache, the average latency is about half what it took the RX 5700 from the previous generation to collect data. The RX 6800 also manages to achieve lower overall latency to GDDR6 as a result of the higher frequencies of both the graphics engine and data fabric. When we combine the very low latency from a cache hit with the less common cache miss and memory access, we get a 34% average reduction in memory latency, again contributing to higher performance at lower power. These benefits are particularly visible in low power environments such as notebooks, where our RDNA 2 products are able to deliver excellent performance while working with narrow, low power memory interfaces. Looking broadly at the overall performance per watt achievement of RDNA 2 compared to the previous generation, we can see that the original RDNA architecture delivered a 50% performance per watt improvement compared to our GCN designs, with about half of that coming from the 14 nanometer to 7 nanometer process transition. RDNA 2 delivered another comparable performance per watt improvement, but this time in the same process technology, which is a true testament to the work and innovation of our architects and engineers, embracing plenty of challenges, but finding a way to navigate through them. The improvements were split between the areas that we've talked about, and the infinity cache and its combination of high bandwidth at low power was a key lever in the final attainment, as it allowed us to extract more of the frequency inherent in the design. Finally, I'll touch just briefly on some of the technical aspects of the feature set that we developed for RDNA 2. Our choices here came about as a result both of our own research and discussions with our partners in determining important future directions and capabilities for next generation rendering. Full exploration of the feature set would be out of scope for this presentation, but just as we had core principles in our quest for performance attainment, I think there are also clear directions visible in the feature additions that were eventually chosen. I think it's safe to say that the overall number of additions that we made represent one of the largest single generation increases in capability of recent years. and it will take some time before all of these new methods can be fully exploited, although the presence of these features in gaming consoles will clearly assist in their adoption. Taken broadly, the feature set can be seen to expand the capabilities of world building, with mesh shaders and sampler feedback both key ingredients in enabling richer and more detailed environments, streamlining the process of rendering detailed geometry and textures, and providing seamless ways to pull in large amounts of data from dense storage to be visualized. Our implementation of ray tracing acceleration was designed to provide high levels of flexibility while integrating seamlessly with our compute and rasterization hardware, in line with our vision for RDNA 2 as being a truly flexible platform for developers to use to build out their vision. With variable rate shading, we decouple the rendering resolution from the shading resolution, recognizing that not all surfaces need to be shaded with equal detail to produce a pleasing visual result. So I'll just talk a bit further on the implementation of ray tracing and variable rate shading to highlight some aspects of our design. For ray tracing, a key goal for us was that the architecture needed to be highly efficient so that it could be deployed in any RDNA 2 device without adding large overhead. We viewed it as vital to encourage adoption by putting effective acceleration into the broadest possible range of devices, with flexible capabilities that would encourage experimentation and discovery of new techniques to extend the reach of ray tracing experiences. As such, our implementation is tightly integrated into the compute units of the RDNA 2 shader architecture. Our ray accelerators can be invoked from any shader stage at any time, and the process of ray tracing maximizes use of the existing shader resources for ray traversal and stack management, streamlining the implementation. We chose to provision for 4 box tests and 1 triangle test per compute unit per clock to balance the throughput against the results that we were seeing for traversal through complex bounding volume hierarchies. This implementation moves significant amounts of potentially divergent ray tracing work out of the shader core and into the ray accelerators, providing massive acceleration for these operations, while the shader itself can be used to implement flexible traversal loops to handle stepping through the BVH, along with shading the final ray results. The implementation also consumes relatively little power, and this allows us to exploit the high frequency capability of RDNA 2 to further accelerate traversal and ray shading. Moving back to modern rasterization techniques, these clearly still provide a compelling and highly cost-effective method of creating images on screen, with high levels of detail and realism. And our aim for the RDNA 2 platform was for it to provide a useful toolkit, whatever route developers might choose to create their worlds. Variable rate shading, decoupling the pixel density from the shading density, provides a key method for developers to accelerate rasterization techniques while retaining high quality. But in implementing such a feature, the balance is very important. If a feature is not intuitive and predictable in its behavior, then its path to adoption becomes harder and the payoff for developers is reduced. This makes it an interesting feature to examine, as while there are many ways it can be implemented in hardware and a broad range of potential capabilities, maximizing the usefulness of the technique in practice was our key focus. Our implementation of VRS centered on providing very fine and flexible control of the shading rate, with a unique rate specified for every 8x8 pixel region. This fine spatial granularity makes it easier to unambiguously select the most appropriate shading rate, and thus makes it easier to extract both high quality and performance. The RDNA 2 implementation also introduces very few overheads into the rendering process and aims to scale in performance exactly as developers would expect, so that for a given shading rate, complex shaders will naturally scale in ratio to the reduction of shading, without unexpected limitations. We considered additional capabilities for the design, such as adding more coarse shading rates, but felt that these did not really deliver much added value. It's naturally increasingly difficult to exploit coarser shading rates without introducing visual artifacts. And in addition to this, they will then tend to offer incrementally less improvements if they can only be applied infrequently. Today, this work has led to the delivery of multiple RDNA 2 products into the market, with each of these products being a unique expression of the underlying architecture. The table here shows the flexibility of the design in adapting to particular market segments and targeted user experiences, independently varying such elements as the core configuration, cache size, and memory bandwidth to optimize for the focus area for each part, while maintaining the full graphics feature set in every product. At the top, we have the 6800 and 6900 series targeted for the highest end gaming experiences at 4K resolutions. Below that, the 6700 series makes adjustments to the cache and memory hierarchy to tune the architecture in line with delivering uncompromised gaming in 1440p, while the reduced core configuration also allows us to drive to higher sustained frequencies while maintaining efficiency. Most recently, we released the latest member of the family with the 6600 XT, with a focus on high refresh rate 1080p gaming. The full range of the design's frequency attainment and its breadth of impact can be seen here, with our RDNA 2 GPUs regularly hitting clock speeds with standard air cooling that previous generations of GPU required exotic cooling solutions to achieve. The goal of the RDNA 2 architecture for us was to be the best interpretation of our vision of the next generation of consumer GPU. We set aggressive targets for our teams with clear priorities, and the result is an innovative architecture that takes the bedrock that was established with RDNA and improves in every dimension, forming a platform that can underpin all of the amazing gaming experiences that we'll see in upcoming years. As engineers, we're always looking for ways we can improve further, and we find new and higher targets to shoot for. But in architecting RDNA 2, I believe that the core principles that we established served us well, with a result that's focused, balanced, and coherent, while still breaking plenty of new ground. I'd like to thank the organizers at Hot Chips for giving me the opportunity to share some of the journey of creating RDNA 2. There were plenty of challenges along the way, but I'm thrilled to have been able to be here to represent the achievements of our team at AMD. This concludes my overview of RDNA 2. I hope you found it informative and that it's provided some useful insights into the design. Thank you.
Now we move on to Q&A session. So first question comes from David Cantor, ML Commons. Can you help us understand the motivation for software BVH traversal instead of hardware implementation?
Yes, so again, I'd just like to thank Hot Chips again for giving me this opportunity to talk about the design. Yeah, so it's a complicated question. Ray tracing is a new thing. Developers are going to take some time to get used to it and to build up the use of ray tracing in their games. For us, the view, we were looking at what would be a flexible implementation, and also, as I stated in the presentation, we were really looking at maximizing the reuse in design as much as possible. BVH traversal is also something where customized traversal is an interesting thing to do, and obviously you want a highly flexible engine to do that on, which we already had with our compute units. So when we were evaluating where to spend effort in the design and which pieces gave the highest value in terms of accelerating them, that was really what was driving our decision-making process there. We believed that it was important to have high flexibility, particularly with the focused places where we were going to put the RDNA 2 architecture. And so that led us to deciding to do the traversal in the shaders and actually, reuse, as I stated, in the slides of the presentation, reuse some of our existing resources in the shaders so that we weren't duplicating those for the new capabilities.
Okay, next question from Yahya Sotabe, Intel. Why didn't you stack Vcache on Infinity Cache similar to Zen 3?
Well, I'm not going to talk about those areas. We made specific decisions in terms of with our design. We were really looking at that stage at it being on chip, and that was what we evaluated. We were evaluating the benefits of the cache versus the wider memory interface that we were going to put on die. And we were already going to put a very large cache on this design. So, in terms of looking at the technologies available, and when we were coming to market, the main thing was to make the right decision to bring the product into the market with the right balance of cost and performance. And that led us to the on-chip cache.
There's another cache-related question from Vijay Thakkar, Georgia Tech and NVIDIA. What is the organization for LLC and ways, sector, etc.?
Okay. For the Infinity Cache. Yeah, so that's quite detailed. I don't know that I have the exact numbers to hand, and I'm not sure we've disclosed them. And it's also something that could vary from product to product. So I don't think there's necessarily one answer to that, and I also don't want to give out incorrect information there. But I'll check, and I can always follow up in the Slack with that information. So I will double check and make sure I'm not giving out the wrong thing.
Okay, thank you. Next question from Omar Darbaz and NVIDIA. What percentage of RDNA to TDP is attributable to the collection of CUs, and what's the remaining TDP split look like?
Okay. Yeah, so generally in these large GPU designs, you would expect when you're under a high workload, the majority of the power is dissipated in the CUs. The exact breakdown obviously is going to vary from workload to workload. I mean, if I was trying to break it down somewhat in ratio, you start with the CUs are the largest component, and they can certainly, I believe, exceed 50% of the total power draw quite easily, depending on what you put on it. Then going down from there, it would be sort of the graphics common blocks. So, the rasterizer, L2 cache, the command processor, basically the hub of the design. Then I think basically we would be looking at the DRAM interface being the next highest. And I think the DRAM interface would normally be, again, depending on the workload, would be competing with the sort of graphics hub for the next highest power draw. But again, with the inclusion of the Infinity cache, we sort of changed that ratio a bit because we went with a narrower memory interface than we would normally have, and also at relatively modest, relatively speaking, speeds. So that it would be then the DRAM interface and then the cache, the Infinity cache after that, I think would be the order of the things. I'm not sure that's 100% true, and it'll vary from application and workload to workload, but I think that's sort of a high-level view of how it will break down.
Okay, next question from Enrique De Lucas, Imagination Technologies. You commented that 8x8 pixels is the smallest VRS region to define a shading rate. Do you support other sizes? Which is the bigger region you support for VRS?
Well, so 8x8 is the native region size we support. So it's the smallest region size, but obviously you can synthesize larger region sizes out of 8x8 chunks. So any larger region size could effectively be supported as long as it's as long as you can divide it into 8x8 blocks.
Okay, next question also comes from Ian Curtis on Tech. Can you talk about RDNA 2 inside the Steam Deck, Van Gogh APU? Anything special there?
No, I mean, I can't really talk about the detailed implementations of parts with our partners. I think you'd have to refer to the publicly available information regarding that design.
Okay, another question from Tom from Moore's Law is Dead. Moving forward, does AMD intend to focus on slight boosts to memory like simply faster GDDR6 with next-gen products, or is memory bandwidth a lesser focus than heavily adding to and improving the Infinity cache further? What's the focus on next-gen bandwidth improvement? Scaling up Infinity cache, optimizing it, or scaling up the GDDR HVM bandwidth?
Well, I'm sure you understand that I can't talk about future products. From a broad scheme of things, as I stated in the presentation, right, whenever we embark on a new design, we go back and we have to revisit all of these areas. How are we going to get the throughput of the core? How are we going to get bandwidth delivery to the core? So you can, the memory interface and the types of memory available will always be a piece of that. And what we've done with the Infinity cache, we've introduced another piece and another part in our toolkit to deliver that what we would target as being the most optimal balance of those things. So I can't say that there's a particular area of focus, and obviously I can't talk about exactly what's going to happen in future products, but we've developed these technologies and they all form part of our toolkit for future hardware.
No problem. Last question from Amarveer Chana on no affiliation. Given RDNA 2 cards have achieved close to or higher than 3 GHz core clock rates, while the L3 cache has been marketed at where is it? Just lost the question. Sorry. Yeah, it's just asking whether oh man, this question just disappeared somewhere.
I think it was one of the first questions in Slack when I was looking
right. You probably saw it. Yeah. So the question is that why this difference, right? The clock difference. Can you go higher?
Can we go higher?
Yeah, the memory clock is 1.9 something, and this is 3 gigahertz. So.
Well, so obviously we built the product to fit within a certain range of frequencies, and and with any of these products, there's sort of a range of interest where they're going to be most efficient or where they're going to hit our goals for the program. But that's rarely kind of the absolute limits of the hardware, and overclockers then take the hardware, and as we've seen, I've obviously watched online. It's always very interesting to me to see what people are doing with my products. And I've seen overclockers pushing the frequencies up higher than what we ship in the products using the tools available. So and we obviously characterize our parts very carefully, right? Any company is going to do that. So we have a very good idea of what the parts are capable of, where the different clock frequencies can reach. So for our products, we built them and we set the ratios between those clocks. Like I said, some of it is sort of in some level of fixed ratio that we've regarded as being the optimum point. But as I said, the frequencies can change independently, right? So we have our fabric clock, which has the infinity for the infinity fabric and the infinity cache, right? Which is one clock domain, and then we have the graphics clock, which is the one hitting, in these overclocking experiments up near the 3 gigahertz mark. And so normally you would expect those to be in some kind of ratio, but again, the hardware, we look at what's happening in the current workload, and that ratio is altered, as I said in the presentation. So depending on if we're seeing ourselves being memory bound and if there could be a benefit to pushing up the clock for the cache, then that's a decision that will be made at a fine granularity to extract more performance from the workload. Whether we push these frequencies higher in future products, again, that's a future product question. But you can see the capabilities of the hardware from what's out there today, I guess. So
no problem. I think we covered most of the questions, and there may be some more. So please take a look when you get a chance.
Sure, I will take a look at the Slack channel. And like I said, if there are aspects of the questions that I wasn't able to answer here, I'll try and fill them in and provide more answers there.
No problem. Thank you. Thank you so much.
Thank you very much.
Yeah. Okay, so now we, after covering 2 GPUs, we now move on to the third talk in our session, and this one comes from on video coding unit accelerator from Google. And we have 2 speakers this time, Aki Kuusela and Clint Smullen. Aki is an engineering manager at Google's Devices and Services unit. At Google, he has worked on both data center and consumer chips, including the VCU and recently announced Google Tensor SoC. Joining Aki is Clint, a system architect in Google's technical infrastructure unit. He has worked on accelerator systems for Brain, Go Cloud, Stadia, YouTube, and others. So Aki and Clint, take it over.
Good afternoon. My name is Aki Kuusela, and I will be talking today with my colleague Clint Smullen about Google's Video Coding Unit, or VCU. I will start with the motivation and describe the architecture and design of the video encoder core, which is the heart of the VCU chip. I will then pass over to Clint, who will talk about chip, board, and rack design, as well as the software and performance comparisons. But first, let's look at the trends that demonstrate the need for a VCU. Video today contributes over 60% of the global internet traffic, and the growth of video has been further accelerated by the coronavirus pandemic. We see the growth across the board, from video streaming to video calls to the emerging cloud gaming, In addition to the amount of streaming events growing, also the amount of data transferred in each event is on the rise. In order to sustain the higher resolutions and frame rate requirements of video, we have to develop better video compression algorithms. With the improved compression efficiency, however, comes greatly increased complexity. For example, if we compare the VP9 from 2013 to the decade-older H.264, the time to encode videos in software has grown to 10x. The more recent AV1 format from 2018 is already 200 times more time-consuming than the H.264. If we further compound this effect with the increase in resolution and frame rate for the top quality video, we can see that the time to encode a video from 2003 to 2018 has grown 8,000-fold. It is very obvious that the CPU performance improvement has not kept up with this massive complexity growth. And to keep our video services running smoothly, we had to consider warehouse scale acceleration. We also knew things would not be getting any better with the next generation of compression formats. So why develop our own video chips? If we look at typical hardware video encoders in the market, while they do claim supporting modern video formats, typically the implementations are heavily optimized for low costs at the expense of video compression efficiency. In fact, if we upload a video recorded on a phone today to YouTube and transcode it with our VCU, we can reduce the video's bitrate by 5 times while maintaining the original quality and format. In addition to the general lack of encoders without cost trade-off, there were also other things we could not find available in off-the-shelf offering. First of all, there were no VP9 encoders available. For each decoded video frame, we wanted to be able to encode tens of different versions with changing resolution and format, a feature that we call multi-output transcoding. We also wanted to be able to optimize the compression efficiency of the video encoder based on the real-time requirements and time available for each encode. And finally, we wanted to have full access to all quality control algorithms, such as bitrate allocation and group of pictures selection. So, with our no compromises implementation, we were able to get near parity to software-based encoding quality. When we deployed the VCUs in our data centers, you can see how YouTube's CPU computing cycles could be dramatically cut down. Next, I will describe the architecture of the video encoder. The VCU encoder core supports H.264 and VP9 formats at up to 4K, 60 FPS per each core. All coding tools specified by both formats were fully implemented in hardware. Starting with the post-processor, which is a high-quality pixel engine in charge of things like color space conversions, cropping, scaling, and rotation. It can be used in pipeline with the encoder or as a standalone operation. Going next to temporal filter. The VP9 format has the capability of inserting synthetic reference frames called alternate reference frames into the bitstream that are decoded by the client but are not displayed, which significantly improves the compression efficiency. This is one example of a coding tool that was not available in any hardware implementation before ours. The motion search and rate distortion optimization engine were carefully designed to support variable throughput so that we could find better prediction candidates if we had more time to spend. This includes adjusting the size of the motion search window, the number of reference frames searched, as well as the number of RDO candidates. On the reconstruction path, we also implemented RD-optimal trellis-like quantization and the collection of various image and compression statistics and frame PSNR to assist our 2-pass and bitrate control encoding algorithms. Our encoder can read up to 4 frames and write 1 during the processing of each frame. As DRAM bandwidth was one of the major restrictions in defining how many encoder cores we could have in a chip, we included a very efficient lossless frame buffer compression scheme that allowed us to increase their number. And finally, we designed the core in such a way that we have hundreds of programmable knobs for optimizing and tuning the encoder performance post-tape-out. Next, I will briefly describe our design flow. As an experienced user of C++-based high-level synthesis, our team also wanted to use HLS on the VCU design. This turned out to be an important decision, allowing us to create a product that was much better than otherwise possible, thanks to the early software-hardware co-design and the ability to iterate fast and often. We could continuously improve the product all the way up to tape-out and beyond. To mention a few of the benefits of HLS that we observed. First of all, there was no need to create a separate algorithmic model of the encoder. The HLS model acted both as the reference model and as the hardware design. So besides the time and effort saved, we could always match our C++ model with our hardware, and there would be no mismatch bugs between the two. Overall, by not writing any Verilog by hand, there was 5 to 10x less code to write and maintain, and given the high abstraction, anyone could easily work on any piece of code and improve the design whether or not they had written the original code. By using a C++-based HLS in particular, we could benefit from all the standard software development tools and workflows, and we could easily tap vast and distributed computing resources without having to worry about running out of simulator licenses. Overall, we estimate we could expose our design to 7 to 8 orders of magnitude higher amount of testing than what we could have done with RTL. By the time we started RTL level verification, 99% of the bugs had already been found and fixed, and there was dramatically less traditional DV effort required in making the product tape-out ready. The other benefit of HLS that we discovered was that as the coding language was at the higher abstraction level, we could leave the mundane hardware state machine design and debugging to the compiler and let the human brain handle the more impactful work. With HLS, we had more time to try out different algorithms and architectures, and we could often find that the original idea was not the best. As changing the design architecture was made so easy, we could loosen the normally tight milestone definitions and allow a little feature creep in. So HLS literally gave us several more months to make the hardware better than what we could have done with our separated algorithm model and RTL design. For future generations, as we move on to a newer technology node and change our clock targets, etc., we do not have to redesign the hardware pipelining. The same C++ will work also there. And with that, I will pass over to Clint Smullen to present the VCU ASIC and system. Thank you.
The demand for video processing continues to increase, but Moore's law has stalled, and accelerators are needed to sustain growth. For Google, accelerators need to be designed for warehouse-scale computing, and we feel the 3 principles here apply to most data center accelerators. For video transcoding, we found the important elements were allowing for a wide range of workload sizes to support maximizing utilization, tolerating errors at the core and ASIC level as reliability is more of a cluster-level property, and using HLS for the core video RTL, as Aki described, paired with software control to provide flexibility to customers. Our workloads range from a single output transcode with 1 encode per decode to a multi-output transcode or MOT with 48 or more encodes per decode. Since most workloads will not saturate a chip, we use isolated firmware-managed queues to help maximize utilization. We support flexibility by keeping all video-related decisions in software, with the firmware only executing simple items such as DMA this data block or run work on an encoder core. Since most of the area performance and capabilities come from the encoder cores, the overall design needed to optimize for their access to memory. While we considered a chip-level cache, it was ineffective given the heterogeneous mix of workloads and the strong locality of the in-core caches. Core counts were chosen to efficiently support large MOTs, and we then sized the DRAM subsystem to provide the necessary bandwidth and capacity. We decided to use LPDDR4 for its bandwidth per byte advantage, with sideband ECC for reliability, and most on-chip memories also use error correction. Error correction helps to improve availability and increases the goodput of the system. Some memories in the encoder core only have error detection due to timing constraints, but we can reset individual cores and fail the affected queues when errors do occur. Encoder cores access to DRAM was the primary concern in making it easy for customers to attain peak performance and utilization. The degree of software control over the quality and speed of the encoder core, combined with bandwidth variability due to the reference compression, led us to be conservative with our NOC design. As shown in the diagram, we aggregate groups of cores into a pair of routers that can individually saturate the roughly 50 gigabytes per second of DRAM bandwidth, which then feed into a single router that interleaves traffic across the 4 DRAM controllers. Looking back, this design was overkill, but it allowed us to lock in the design early and focus on other areas. Looking at the firmware queues, we rely on the stateless operation of the encode and decode cores, allowing them to be reset between operations and freely used for different queues work items. A queue's DRAM allocation is set statically during queue creation, and we use a simple hardware page table at each core's interface to the NOC to provide isolated and virtualized access to the queue's DRAM. A single decoded frame can be used multiple times, and firmware allows explicit dependencies between work items. Practically speaking, software is serializing a DAG of operations into its queue, which is then processed by firmware with bounded look-ahead, relying on parallel queues to maintain high utilization. Moving to the system and rack, we minimized the TCU per VCU ASIC by putting 20 VCUs per system with 2 ASICs per board using bifurcation, 5 boards per PCI Express expansion chassis, and 2 chassis per host, all delivering 200 encoder cores per system. The VCU's average power consumption ended up at the lower end of expectations, so the LPDDR4 temperatures are the primary driver of tray cooling needs. We put as many machines into each rack as space and power allow, and they end up looking similar to the AlphaGo racks that have been previously shown. This graph shows the speed up of our VCU against software on a 2-socket Intel Skylake system doing single output transcoding. While pure SOT workloads are unable to maximize ASIC level utilization, it does represent the maximum system level load using the most concurrent queues and processes, and the linear scaling shows that relying on software does not impact our scalability. For H.264 transcoding, a single VCU matches the speed of the baseline system while using about 1/10 of the system level power. For VP9, a single 20 VCU machine replaces multiple racks of CPU-only systems. At the cluster level, we take advantage of the heterogeneity to fill both reliability and capability gaps. We've previously described the cluster-level scheduler, which can tolerate failures at a queue, ASIC, machine, or even rack level, redistributing and retrying transcodes. Error correction for the DRAM of both the VCU and host system are critical to the availability of such accelerator-dense systems, but the ability to at least detect other forms of errors is an important element in triggering these higher-level retry mechanisms. As the VCU only supports H.264 and VP9, we continue to use CPU processing to support legacy formats along with audio and other unaccelerated processing. While using HLS in the encoder helped provide flexibility and velocity before tape-out, the focus on software control made it easier to improve things after deployment, as shown by the quality gains in this chart. We were also able to boost hardware utilization by using supplemental software decoding on the VCU hosts, as some use cases are hardware decode limited. As mentioned before, each layer of co-design helps to contain errors, letting on and off-node software handle decision-making. In summary, using a software approach was critical both to supporting the quality and feature development in the video core, as well as allowing customer teams to iteratively improve quality and performance. While the rest of the VCU ASIC was not designed with HLS, it was not on the critical path to tape-out, and the goal was to remove bottlenecks in attaining high performance and utilization. A desire for higher density and the ability to handle capability and reliability gaps at the cluster level exemplify how accelerators going into warehouse-scale systems have fundamentally different requirements from other markets. With the VCU, we were finally able to address a need for affordable video transcode acceleration for many products across Google. A system of this scale takes a village, and we want to again thank the numerous teams and people across Google and beyond that made this project a success.
Okay, thank you, Aki and Clint. So let's get to questions now. First question from Joshua Gregory, editor Chips and Cheese. Using VCUs, can a hybrid approach be used in tandem with the ASIC encoder? That is it possible to do some parts like entropy coding and things like temporal rate distortion, etc. on CPU, while the rest is being done on the ASIC if absolute maximum compression efficiency is required?
Okay, I can take that. Basically, we don't think it's viable. Our design is very tightly pipelined, and we did not design any intermediate tap-in or tap-out ports. So in this case, we cannot do hybrid with the VCU.
Okay. Second question also from him, would an FPGA-based design be even better in the long run, or are FPGAs for encoding not flexible enough?
I'll take that one. The real issue is the sheer scale of Google's customers. It really motivates us to go straight to an ASIC, just simply due to the cost and the throughput of FPGAs being unsuitable for at-scale usage.
Okay. Next question from Raghav Kandanahalli, Intel. What is the PCIe card profile which has two VCU chips, like number of PCI lanes and card TDP?
Sure. Google has an in-house bifurcation format we use to deliver two chips on a card. Otherwise, it is functionally a KIM form factor, full height, full length, dual slot board. Like a GPU, it takes an auxiliary power input of up to 300 watts. We designed the board for over 100 watts, but as mentioned in the presentation, post-silicon measurement showed it being a lot lower, but we're not releasing more specific details at this time.
Okay, I can hear some noise, so maybe one of you can take a look. Next question from James Sanders, 451 Research. Will VCU be made available by Google Cloud, assuming it's not presently?
We are always looking to enable unique capabilities in our cloud, but we don't have any announcements to make at this time. If you are interested, please let your TAM know.
Okay. Next question from Amar Vichana, no affiliation. How pervasive do you think coding hardware in C++ will become in the future? Do you think it will be important for up-and-coming students to understand this?
Personally, I definitely think that the HLS is very effective way of designing hardware, and it does cut down a lot of time in the design, and especially in the design verification part. That said, many organizations have a lot of inbuilt expertise in Verilog, and it's kind of hard for organizations to move out from designing Verilog. But I would definitely recommend new companies, new teams to take a close look at HLS.
So just a follow-on question related to that, I had how much performance, just comparing HLS to handwritten Verilog, how much performance are you giving up? And was HLS used for the entire encoder design?
Yes, HLS was used for the entire encoder design. And regarding of how much do we give up, it's a function of time. So when you spend enough time, you can get parity with RTL. And in our case, we were more interested in getting being able to try out a lot of different architectures and algorithms to really find out these bigger picture problems and end-to-end optimization of the system rather than chase for the last flop to get out of the chip. So for our case, HLS was definitely very good, and definitely you can get parity with HLS to handwritten RTL.
Okay, another related question, HLS from Max Corbel, Intel. What HLS compiler software do you use?
We used the Catapult HLS tool from Siemens.
Okay. Manoj Roge, Synopsys. Agree with the benefits of HLS, but curious, what is your experience with RTL quality and whether you would continue the high-level design for design flow for future designs? I think you already answered, but one more time.
Yes, we have been using this flow for almost 10 years, and I think it's just getting more and more improved. And it's really nice that one day you get an upgrade from the compiler company, and suddenly your design is smaller and faster. So that's pretty nice thing to have.
Okay. Ian Curtis, Amtech. On-die caches are ECC, all are sected, like singular correction, download detection.
I'll take this. So yeah, I mentioned in the talk where possible we use SecDed at full correction and double error detection, but there are some SRAMs on the chip, in particular inside the encoder core, where timing did not allow for correction on those paths, so we only do detection. But fortunately, because they're confined to the codec core, if an error does occur, we can stop the affected job, reset the core, reset the job, etc.
Okay. Another question from him: can a single VCU handle an 8K60 decode and MOT mod?
Yeah, I guess from a format standpoint, VP9, I don't think profile goes up to 8K, but in terms of just raw throughput, it can get there. But given that there's no VP9 profile that I know of, maybe Aki knows, there's no VP9 formal profile for 8K. While throughput it can get there, there's not actually a specified way of accessing that capability.
That's right, yes.
Okay, so the related question also from Ian at Cutlass at Amtech. Ian Cutlass, where do we sit with other codecs? Can besides H.64 and VP9, or should other chips be on the way focus on other formats? Would it be best to make chips iterative, or that's a question. Other codecs.
Yeah, I don't think we can comment on future formats, but Google is part of the Alliance for Open Media, and we are definitely very heavily involved in AV1 and in the development of the next generation AV2.
Okay, Nick Loads, unaffiliated. How are audio streams handled in the data flow?
Yeah, at this time, so again, coming back to the warehouse scale computer, really the stream is broken down into its constituent components, which might even mean that the video stream is chopped up into chunks or audio is chopped up into chunks, etc., and farmed out to a bunch of different worker nodes. So in general, audio will be processed on CU node, and so the VCU itself does not touch the audio processing.
Okay, next question from Jayaprakash Palachandran is one of the slides, slide 22. What does X4 and X6 refer to with respect to LPDDR memories?
We have 4 memory controllers, but we made the decision to go with sideband ECC, so we are actually ending up using 6 different LPDDR4 packages. That's likely what it's been referenced to.
Okay. Okay, I think maybe last question from Yayas at Intel. Are you using RISC-V anywhere in your design?
We are not at this time, no.
Okay, since we have a minute, just one more question from David Cantor, ML comments. Is latency or jitter a top-level design constraint, or are you primarily throughput-focused?
Do you want to start this, Aki?
Sure. From the video codec point of view, we are throughput focused, so the time to pass the data through the encoder doesn't matter, but the throughput matters. On the other hand, if the question is about whether we care about real time rather than 2-pass encoding, we do care about both cases. So there are YouTube Live, for example, that also wants to do low latency encoding.
Okay, I think that does it. Thank you so much.
Sure. Yep.
Yeah,
Great.
thank you, Aki and Clint. So now we move on to the last talk of our session. And we did 2 graphics chips, 1 video chip, and now we move out of data center all the way to edge. And this 4th and final talk of our session is an edge processor, and it comes from Xilinx. Speaker is Juanjo Noguera. Juanjo joined Xilinx CTO office in 2006, and he's now part of the Silicon Architecture Group in the Xilinx Product Development Organization. So, Juanjo.
Thanks for the introduction, Pradeep. It's a pleasure to be here. I'm privileged and an honor of giving this presentation at the Hot Chips conference this year. First of all, I would like to acknowledge all the key and outstanding contributions from multiple engineering teams from Xilinx. And today I will be talking about Xilinx 7nm edge processors. This slide covers the 3 key points that I would like you to remember out of this presentation. The first one is that we are introducing 2 devices optimized for edge applications, edge inference applications. These 2 devices are part of the Xilinx Versal AI Edge family. The second point is the concept of accelerating the whole application. ML inference is only one task in a complete application at the edge. It's important to remember all the other tasks that are required for implementing the full application. And today I'll show this concept on 2 specific use cases and how these 2 use cases map on the 2 specific devices that we are introducing today. Finally, the third bullet is this: we are introducing the new AI/ML architecture. This AI/ML architecture is optimized for inference and is the 2nd generation architecture after the 1st generation AI that was introduced at this conference a couple of years ago. Now, let me just give a super high-level overview of typical edge applications and what are the requirements for inference, the use cases, and the requirements. As you can see, there are multiple applications that are shown in this slide where edge inference is required. This could go from automotive applications to industrial applications, to medical imaging applications. One specific use case and application that I would like to emphasize is the smart city use case, because this specific use case is one that I will be using later on in this presentation. Finally, the challenges. All these applications require delivering massive amount of AI compute at very low latency and low power. Now, a very high-level overview of the Xilinx Versal AI Edge family. This family leverages all the key building blocks that have been previously introduced in the Xilinx Versal family. Some of you might remember that in previous hot chip conferences, Xilinx introduced the Xilinx AIE cores and the Versal premium families. In this, and Versal AI Edge is a continuation of that architecture. It integrates programmable logic, ARM processor subsystems, and AI engines. All these tied together using the network on chip. At the bottom of this figure, you can see all the hardened shell with all the specific interfaces that are available in this device. These include, for example, DDR interfaces and PCIe interfaces. One particular aspect that I would like to emphasize, and you can see in this slide, is the video decode unit. This video decode unit will be explained later on in this presentation and how it's being used in the particular use case. And as I said before, we're introducing this AI/ML architecture, the second generation AI architecture, optimized for ML inference. Now let's go a little bit more, one level down into the details of the two devices that we are optimizing or that we are introducing today. As you can see, there are two devices, one more towards the low end and one device more towards the mid-range. In this table, you can see the different figures of merit in these two particular devices. You can see, for example, the peak performance at the device level for int8 precision and also for int4 precision. The last row shows the projected power estimations for these two particular devices. As you can see, the smaller device is targeting somewhere in the range of 15 to 20 watts, while the mid-range device, the VE2802, is aiming at the 75 watts use case. As you can see, the number of AI/ML tiles can range from tens of tiles to hundreds of tiles. In addition, you can find the Xilinx programmable logic optimized for 7 nanometers and the the A72s and all the ARM-based processor subsystem that is present in the Versal family. Maybe two particular aspects that I would like to emphasize is that this mid-range device, as you can see in this table, includes the video decode unit. And also, it integrates a PCIe Gen 5 hardened controller with integrated DMA for coherency with host processor. These two devices can be optimized for different use cases, ranging from the very low-end, low-power use cases to the high-end, or let's say 75 watts, half-height, half-length PCIe form factors as an accelerator card. This slide is also trying to show the same concept, where we show different types of form factors with a required power consumption, and we can see that we can go from 5 to 10 watts on one end to 300, 400 watts at the other end of the spectrum. In this particular, as I said in the previous slide, the main goal of the VE2802, the mid-range device, is aiming at the 75-watt half-height, half-length PCIe form factor, while the smaller device is targeting to the 15 to 20 watts use case. Now, as I said before, today we're introducing and providing additional technical details on the AI ML architecture optimized for machine learning. Some of you, as I said before, might be aware of the first generation AI architecture that was introduced a few years ago. In this architecture, we keep the same macro level architecture where we have a two-dimensional array of tiles, and each tile, all of these times interconnected through a high bandwidth streaming interconnect. I'll cover the details of the tiles and the internal structure and interfaces in the following slides. If we go one level down, we have the changes that we are emphasizing in, or what we have done for this architecture is that we have doubled the number of multipliers for int8. So we are doubling the number of multipliers per core. We are adding native support for ML inference optimized data types like int4 and bfloat16. And we are also doubling the local data memory for each of these tiles. This helps in having more data localization for edge inference applications. Finally, and this is a complete new tile that we it's part of this AI ML architecture, is this new memory tile. One memory tile is basically integrates 512 half a megabyte of SRAM, ECC protected, and includes data movers to connect, to interface to the compute tiles and to the Xilinx network on chip. Or specifically, the specific amount of memory tiles, it obviously depends on the device, but in the mid-range device, the total amount, the memory capacity in this memory tile is about 38 megabytes. The capacity is one aspect, but and that adds a lot of value to reduce the external DRAM memory bandwidth and improve the efficiency. But a key aspect of this memory tile is not only the capacity, but the bandwidth that it provides to the compute tiles. We are increasing the amount of compute, so we need to find faster and higher bandwidth interfaces and memory hierarchy to fit all these multipliers. As in the previous architecture, this AI/ML architecture is scalable and modular. And as you have seen in the previous slide, we can adjust the number of AI/ML compute tiles and memory tiles according to the requirements of the device and the use case. This table is maybe one level down comparison of the first generation AI tile architecture, which was optimized for wireless 5G, ML inference, and aerospace and defense applications. As you can see, it has 128 multipliers per tile, but it didn't have native support for bfloat16 or int4. On the other hand, the AI/ML tile that we're introducing today has doubled, as I said before, double the number of int8 multipliers, has 128 bfloat16 multipliers, and 512 int4 multipliers. We have doubled the local data memory, as it was mentioned, and we have integrated the new memory tiles. Both tiles are implemented in a single clock domain that can run up to 1.3 gigahertz in the higher speed grade. Now, if we look one level down at the block diagram and the architecture of the AI/ML tile, what we can see is built out of three main building blocks. One is the AI/ML processor. This is a VLW vector processor with optimized microarchitecture and instruction set for ML inference. It has a local memory, local data memory. This memory is implemented as a multi-bank with multiple banks in order to provide high bandwidth and integrates a micro DMA that enables the movement of data while the core is computing. The final third component of this architecture is the non-blocking streaming interconnect, which provides high bandwidth between the different adjacent tiles. The final interface that I would like to, maybe one more point that I would like to emphasize on this streaming interconnect, these interfaces are built of multiple tracks. And this interconnect supports multiple modes of operations. And I will explain several of the key use cases that drove the requirements of this streaming interconnect. Now, one additional interface at the tile is what we call the cascade interface. This is an interface that is point-to-point directly connected between adjacent tiles. And this provides the functionality where we want to transmit or transfer the intermediate results from one core to the adjacent tile. Now that I have introduced the architecture and the building blocks and the types of interfaces, let me give you a couple of examples of data flow in this architecture. First, I will explain two different examples. These are at the AI array level and how we can compose multiple of these tiles to implement, for example, a matrix multiplication or a convolution that is obviously essential kernel in all these ML inference applications. In this particular example, I will talk first about the data reduction. Let's imagine that we want to implement a functionality where we're going to generate a single output matrix, C, in this example. And this output matrix is computed by doing 4 block-based matrix multiplications where A and B could be the weights and the activations. As you can see in this picture, we would need to do 4 matrix multiplication kernels. And if we implement this on the AIML architecture, we will implement this as 4 AIML tiles connected through the cascade stream directly. So in the end, we will produce only one output matrix. The core has the capability of doing the vector operations, computing the int8, the data vector data compute, but at the same time read from the stream, the cascade stream, and push out to the output stream, cascade stream. So this is one simple example. The other one that I would like to emphasize is this data multicasting, and that's one example that showcases and shows the value of the non-blocking streaming interconnect. Let's assume that in this case, we want to produce multiple outputs. In this case, we want to produce several n number of output matrices. All these matrices will have obviously independent values, but they will share all the weights. So in this particular implementation, we would assume, or we will follow the same approach where we would cascade 4 AI ML tiles to produce one output, and we will have n number of these chains running in parallel to produce these n output results. Each of these tiles will have its own independent data coming in through a stream, but what you can see is that the weights in this particular example can take benefit of the data multicasting capabilities of the streaming interconnect. This significantly reduces the amount of memory bandwidth that is needed in this architecture. Because in this particular example, as you can see, we can read the weights only once and multicast it n times. So it significantly reduces the amount of memory bandwidth and hence reducing the power in this type of applications. Now, this slide is a bit of is another concept of how we would use this architecture, but this time instead of at the array level, at the device level. It's a device level data movement slide. And we show 3 types of data movement. The first one is from external memory, external DDR, through the programmable logic, you might want to do some pre-processing in the programmable logic before the data it's pushed into the scratchpad memory that is implemented in the memory tiles. Once the data is in the memory tiles, it can be transferred to the AI ML compute tiles. So this is one example. The second example is where the data from external memory, external DRAM, can directly go over the NOC, not using any programmable logic resources, directly into the scratchpad memory. And then again, from the scratchpad memory into the compute tiles. And the final one is a very similar data movement pattern, but in this case, it's from external memory and bypassing the scratchpad memory and directly into the compute tiles memory, local memory. So these are 3 types of examples of how the data can be moved in these devices across the chip. Now that we have talked about external memory bandwidth, let me emphasize another feature that I mentioned earlier that is available in the AI/ML architecture. This is compression and sparsity. In this particular plot, let me show the benefit of this feature, what this brings us in terms of a particular use case, which is a ResNet 50 HD use case, where we have int8 quantized weights and int8 activations. This slide shows the compression factor that we can achieve in the architecture. And on the x-axis, we show all the different layers in ResNet 50. We plot the minimum, maximum, and average compression factor. As you can see, it's pretty similar. And I guess the high-level summary of this slide is that with using the compression feature available in the AI/ML architecture, we can cut the memory bandwidth by about 50% in average. As you can see, in the final layers, there is the compression factor can be higher. Now, let me wrap up a bit on the AI/ML architecture. I guess the main goal of this slide is to show the key architectural features that make this architecture high efficiency, high compute efficiency. The first one is the as I said before, is the VLIW vector processor. Again, the instruction set and microarchitecture are optimized for achieving high efficiency. This example is we show a particular matrix multiplication kernel where it can achieve 90 to 95% of the theoretical peak performance at the core level. The other aspect that I mentioned, and I want to emphasize it again because it's really, really important, is the adaptable non-blocking interconnect. This provides flexible data movement architecture, avoids bottlenecks, and it has multiple modes of operation, like, for example, the one that I explained about data multicasting that helps in reducing the external memory bandwidth. The second point that I would like to emphasize is the memory hierarchy. As you can see, this is a distribute, but at the same time shareable memory hierarchy with high bandwidth. There are no caches in this architecture, and the data is not replicated. If for whatever reason you need additional memory or additional memory hierarchy, you can always extend the memory to use the programmable logic resources like VRAMs and URAMs. Finally, the last bullet is just to emphasize again, is the capability of doing compute and data communication and data transfers in parallel. This is enabled by all the micro DMAs that are available throughout the architecture, and that I mentioned earlier as well. So the goal is to keep all the compute as busy as it can. And the final slide is just trying to emphasize the concept of the memory hierarchy and the interconnect. In a traditional multi-core architecture, you have the multiple levels of cache memory where the data is replicated. You have multiple copies of the same data throughout the memory hierarchy. In the AI/ML architecture, because the memory is distributed, and there are no caches, there is no data replication. And at the same time, this reduces the bandwidth, because if you need to move all this data through the memory hierarchy, it requires additional bandwidth. And the final one is the shared interconnect that is available in the traditional multi-core architectures, while in this the interconnect that is available in the AI/ML architecture is more point-to-point dedicated streaming non-blocking interconnect, providing deterministic performance and throughput. Now, let me switch topics and let's talk about how to program these architectures. I have two slides. This first slide covers the programming of the architecture at the C++ level. As we have introduced today, we have, as you know, there are multiple architectures. We have the first generation AI architecture, and today we are introducing this AI/ML architecture, the second generation. These architectures have different underlying hardware and underlying capabilities, but both can run, for example, ML inference kernels. So what we don't want is the users having to program each different architecture independently. So what we're introducing and we're proposing, and that's what is already in development, is a portable common high-level API across the AI architecture. This API that is shown in this picture is the interface that will be used to program current and future generations of the AI architecture. This interface is the interface that we'll use by the kernels developed by the customers, writing in C and C++, or the internal teams developing libraries. They all will use the same programming interface. This obviously will be a backwards compatible interface. It will evolve. New devices will add new functionality, so this abstraction will evolve and add support for the new capabilities. And it's also efficient. Efficient in the sense that the applications can be optimized to maximize the compute efficiency available in the hardware. This AI API is implemented as a C++ header-only library, and it will be released in upcoming releases of the Xilinx software stack. Now, if we move up in the software stack and you don't want to program these architectures at the C++ level, you obviously supporting full AI software stack is a must. Xilinx has the AI software stack. It's called Vitis AI. And this picture, this slide just tries to give you a very high-level overview of the Vitis AI software stack. As you can see, it supports all these ML frameworks that you can see in this slide. It provides multiple tools like optimizers, quantizers, profilers, libraries that will be used to program different Versal architectures. The Versal AI core series is already available in the market and is in production. And the AI Versal Edge devices is the ones that we're introducing today. The customers and the users can start developing applications at the framework level, targeting the Versal AI core series, and then take exactly the same model and run it on the future Versal AI Edge devices. Now, if I move on from the programming topic, I want to now switch to the whole, the topic that I mentioned at the beginning, the whole application acceleration, and I want to provide two particular examples. One is a smart city use case. There are multiple examples where you have a smart retail, a smart city use cases, a smart hospital. There are multiple of these examples and use cases and applications. In this block diagram, I try to make a very high-level pipeline of a generic application. In this application, what you can see is you receive from the cameras, you might receive multiple streams of video encoded data. This encoded data comes at, for example, HD resolution, and the first thing you want to do is to scale the image so it can go and provide as an input to an object detection network, ML inference task. This could be, for example, a YOLO-V3 network. Once we have detected the objects in the image, there is another video scaler that is required to feed these images to the multiple instances of a classification network, like in this example, ResNet50. You can see that there is a change in the input resolution from 416 times 416 to 224 times 224. Finally, based on the objects that and the classification and the information generated, there is a decision-making task. Now, this pipeline and this example as an application pipeline, I think, clearly shows the need for to focus on the whole application acceleration. It's not only important to, obviously, it's important to have very efficient ML inference, but you need to be concerned how to have a balanced pipeline and how to have the proper hardware and building blocks that will fit all this massive amount of inference compute. And for example, in the mid-range device that I have mentioned before, with the more than 300 AI ML tiles, what we realized is that to fit all this amount of AI ML inference compute, it would take a lot of resources to implement the video decoder units in programmable logic. So what we have done, and that's one of the reasons why we hardened the video decode units. The video decode unit can support up to 32 1080p 30 video streams. Now, again, just to emphasize, it's just you need to think and accelerate the complete pipeline from video decode to decision making. The second example is an example targeting the low-end device, the 15 to 20 watts device that I mentioned before. It's targeting an automotive use case, and it follows kind of a similar concept. No, you have all the interfaces. You could have cameras. You can have radar, lidar workloads. Interfaces, sensors, and you want to use the programmable logic to do the sensor fusion for all these sensors. This data then will feed into the AI engines for object detection and classification, and finally the results will be sent to the ARM processor subsystem. So again, whole application acceleration from sensors to AI to real-time control. Maybe one quick slide about performance per watt results. These results show benchmarks for two devices, the small device and the mid-range device. Both show the ResNet50 with batch of one. Batch of one is because of the low latency. In all these edge applications, we want to have low latency, and that's why we picked batch of one. And what we can see is that both devices provide between 3 to 4x performance per watt improvement versus the other devices. Just to wrap up this talk as a summary, let me just emphasize the key 3 points that I wanted you to remember out of this talk. The first one is that the two Xilinx devices that Xilinx has introduced as part of the Versal AI Edge family. This is based on the 7-nanometer Versal architecture. There is a low-end device targeting a small form factor, somewhere between 15 to 20 watts, and there is a mid-range device targeting the half-height, half-length PCIe form factor of 75 watts. The two use cases that I have just described show the concept of the whole application acceleration, and I've showed the example of the smart city and automotive applications. Finally, we have introduced this AI/ML architecture, which is the second generation AI architecture optimized for machine learning inference. This architecture provides major improvements in performance per watt and has architectural features optimized for inference like data types, memory hierarchy, and sparsity. Thanks for your attention.
Thank you, Juanjo. I think we're a little bit short on time, so I'll just pick a few questions. Okay. First question for you from Jan Gray Research. In revising the AI engine instruction set for ML inference, did you consider implementing block floating point support as used in Microsoft Brainwave in Acronic Speedster or the Stratix 10 tensor block?
This AI architecture doesn't support block floating point. It supports bfloat 16.
Okay. Related question from David Cantor, ML Commons. Do you support FP16?
No, there is no FP16 in this AI ML architecture.
Okay. One more numeric question from Anujan Verma, UC. Does the core support stochastic rounding?
There are a lot of different rounding modes and saturation modes. Yeah, and this I should defer to the data sheet and the information, but the short answer is yes.
Stochastic rounding is supported. Okay. And how do you deal with sparse data? I don't know if it's a simple question to answer.
Well, we have a super simple compression scheme focusing on zero compression. And that's the one that we have implemented in this architecture. We wanted to start simple and keeping the hardware, limited the hardware impact for this feature. So it's just basically zero compression capabilities.
Okay. Another question from Anirban Ghosh and NVIDIA. If 90%, 95% of the math ops and overall ops happen in the programmable AI tiles, how much value does the traditional FPGA part of the chip add? Do you envision a product where all of the die area is devoted to AIE? Basically, the question is, what ops do you place on the FPGA side? Is there still an FPGA here?
Absolutely, yes. I obviously did a bad job in this presentation. If the concept of the whole application acceleration is not clear, you have, first of all, you need to have interfaces to all the sensors in these edge type of applications, and these sensors keep changing, keep evolving. The other is it's not the ML inference, you need to do the pre-processing and post-processing, you need to do color space conversions, you need to do video scalers, and all this functionality is implemented in the programmable logic, as shown in the slides in the use cases that I shown today.
Okay, last question, and then you can, is just, have you designed the VLIW core and compiler or licensed it as IP?
All the instruction set and the microarchitecture is Xilinx proprietary. It's not licensed. The core is not licensed. It's Xilinx proprietary, built from the ground up.
Okay, thank you. That should do it. Sorry, we are a little behind in this, so I think we have run out of time now. And please go to the Slack channel. There are more questions for you, Juanjo. And thank you so much.
Thanks to you, Pradeep. Thank you so much. Thanks for all the questions, and we'll follow up.